So just a couple of announcements before we get started. Announcement number one, the deadline for 8/4 through 8/6 material has been extended to Sunday. After Sunday, anything not turned in will go to a 0. And you won't have the ability to turn it in. Next week, we will have a review and a quiz on 9/1 through 9/3. So again, another opportunity to improve on your score, your grade, or maintain your good grade if you're there already. So take advantage of that. We'll have, like I said, a little review session, and then you will have time to complete the review and more than likely the quiz if you just stick on Schoology for the class period on Tuesday next week for your class. So got that to look forward to. The last bit of material that we'll have on that quiz is simplifying radical expressions. And we're going to look at a couple different ways to do that. So one of the things I want to emphasize is simplifying a radical expression is not just typing it into your calculator and getting a decimal answer. That would be approximating radical expressions. And that's not what we want. We want the exact value. So that's what we're going to work on today. Like I said, I will show you two different methods that you can use to do that. Easy for me to say. All right. So this is page 13 of your packet. So if you have your packet, that's where you should be. So two different methods that can be used to simplify square roots and radicals. The first one involves making a factor tree, and the second method involves finding perfect square factors. So the factor tree method, make a factor tree for the number under the square root. Keep breaking down the factors until you are down to all prime numbers. So remember, prime numbers are numbers evenly divisible by 1 and themselves, and that's it. Excuse me. Circle the pairs of factors. So anytime you have two factors that are the same, we're going to circle it. Box the leftover numbers that could not be paired. Pairs go outside of the radical. That's the square root symbol, often called the radical. One number per pair. The numbers that are in the boxes go under the radical. And then you multiply the factors outside the radical and inside the radical to simplify your expression. So you'll multiply together all the numbers that are outside. That'll give you the number that goes outside the radical. Then you'll multiply all the numbers inside to give you the number that goes inside the radical. Again, one of those things, I think seeing an example will make it much easier than trying to figure it out from just being told what you're doing. So the prime numbers, 2, 3, 5, 7, 11, 13, and they go on. So I always start with my lowest prime. I always check 2 first. 80 is even, so 2 is a factor. 2 and 40. Now I've got my prime number 2. I don't have to worry about that anymore. 40 is even, so 2 times 20 is 40. Again, I've got that prime number 2. 20 is even, so 2 is a factor. 2 and 10. And 10 is even, so 2 is a factor. 2 and 5. So I'm going to circle a pair of 2s and another pair of 2s. Those will be my perfect square factors. They'll go outside of the square root symbol. And the 5 is the only factor that couldn't be paired up. So that's going to go inside the radical. So my answer is going to be 2 times 2. So 1, 2 comes from this pair. 1, 2 comes from this pair. And underneath the square root, I just have that 5. So 2 times 2 is 4, square root 5. So the square root of 80 in its simplified form is 4 square root 5. Sorry, 4 square root 5. And there's my answer. So the other method of simplifying, if you just see a radical expression as an expression that contains a square root or radical, it is simplified when it contains no perfect square factors other than 1, because we can't ever divide out and get rid of that factor of 1. Simplifying square roots and radicals, again, involves finding perfect squares. So here are the first 20 perfect squares. So if a number is evenly divisible by 1, which all of them are, 1 would be a perfect square factor. If it's evenly divisible by 4, 2 would be a factor, and so on. To be honest, as you're kind of looking to the future maybe a little bit, for the ACT test, which most students take in their junior year, some in their sophomore year, having the first 20 perfect squares memorized is a good thing. Again, I believe the ACT, you have the math portion. I think it's 60 questions and 60 minutes. So anything you can do to save yourself some time would be a good thing. All right. Taking a look then at how we can use these perfect squares to simplify a square root. So what we want to do is we want to find the largest perfect square that evenly divides into the number under the radical. We're going to rewrite that radical as a product of your perfect square from step 1 and whatever you get when you divide the number under the radical by that perfect square. Simplify by taking out the perfect square. And I actually do this even a little bit differently than the method described here. What I like to do is I like to take my square root and break it into 2. Underneath my first square root, I write my perfect square. Underneath my second square root, I write anything left that's a non-perfect square. So for instance, starting with 80, or trying to find the square root of 80, if I go back to my perfect squares, The largest perfect square less than 80 is 64. So that's where I'm going to start. And I'm going to divide and see if 80 is evenly divisible by 64. If it is, then I know I can break it up and I'm done. And I'm going to work my way down. If it's not evenly divisible by 64, I check to see if it's evenly divisible by 49, and then 36, and 25, and 16. And I stop the first time I find a perfect square that it's evenly divisible by. Important that we start with the largest perfect square and work our way down. Don't start with the smaller one and work your way up, because you could miss something. So I try 80 divided by 64. If that comes out as an integer, I put 64 in the left-hand radical and whatever that integer is in the right-hand radical. In this case, 64 doesn't work. So then I try 49. 80 divided by 49 does not give me an integer answer. So after 49, I try 36. 36 doesn't work. 36, I think, is 2.5. It's pretty close, but not quite an integer. So after 36, then I try 25. 25 doesn't work. That gives me 3.2. Again, pretty close, but not quite. After 25 is 16. 80 divided by 16 is 5. That works. So my perfect square is 16. My stuff that's left over, 80 divided by 16, is 5. And now I finish by taking the square root of 16. And again, looking at my list, the square root of 16 is 4. So you can see we get the same answer using both methods, which is good. And it's kind of a personal preference. Which one do you like? I personally use this method with the perfect square. Some people don't like the perfect square method. They use the factor tree method. Again, they both work. They're both good methods. I will actually do the examples. The first 3 I'm going to do with the factor tree. The last 3 I will do with the perfect square method. So simplify the radical. Square root of 75. First thing I check, is 75 a perfect square? Unfortunately, it's not. So now I break it apart. 75 is not even, so 2 is not going to be a factor. If I add the digits, 7 plus 5 is 12. 12 is evenly divisible by 3, so 3 will be a factor. 3 and 25. For 25, if I add the digits, I get 7. 7 is not evenly divisible by 3. So then I check 5. It ends in a 5, so 5 is a factor. And actually 5 times 5. Circle my factor pairs. Box the ones that don't have a pair. One 5 goes outside, the 3 goes inside. Excuse me. 108, it's even, so 2 is going to be a factor. And 2 times 54. 54 is even, so 2 is a factor. Um, 27 is not even, but if I add 2 plus 7, I get 9. 9 is divisible by 3, so that means 27 is going to be divisible by 3. and 27 divided by 3 is 9. And 9 is divisible by 3, and it's 3 divided by 3. Excuse me. So I have a couple of 2's that can be grouped together, a couple of 3's that can be grouped together, and a 3 that can't be grouped with anything. So in this case, 108, I would take the 2 and the 3 that have pairs, I'm going to multiply those together. And the 3 that doesn't have a pair goes underneath the radical. So we have 6 root 3 for 108. All right. 3 times the square root of 32. Okay, a little something different here. Now we have a number already out front. We just have to remember that we will have to multiply whatever our answer is by 3 when we're done. So the radical part we do the same way. 32 is even, so 2. 32 divided by 2 is 16. 16 is even, so 2 is a factor, 2. And 8. 8 is even, so 2 is a factor, so 2 and 4. 4 is even, so it has 2 as a factor, 2 and 2. Again, circle the pairs. And one of the nice things, if you go from least to greatest prime, your pairs should all be on that diagonal going down. You could have a non-pair there as well, but you will always have your pairs there. So I have this 3, and I have a factor of 2 for my first pair, and a factor of 2 for my second pair, and then the 2 that's in the box goes underneath the radical. 3 times 2 is 6, times 2 more is 12. So there we get 12 square roots of 2. All right. Oh, just 1 second. Again, for these, I'm going to use the perfect square method. So I always start with the perfect square that's less than my given value. So that page in your packet, I would, again, somehow mark it so that it's easy to find and get to. 72, the largest perfect square that's less than 72 is 64. So I try 72 divided by 64, and I don't get a perfect square. I get, I think, 1.125. Then 64, then 49. 49 does not work, and I'm not sure what I get. I just know it's not evenly divisible. 72 is not evenly divisible by 49. By the way, sorry, I should have mentioned this. We already did 108. That's why there's, a line through it. After 49, the next perfect square is 36. 72 divided by 36 is 2. So 36 is a perfect square that evenly divides into 72, and it divides in 2 times. Square root of 36 is 6. And then I have the square root of 2. Letter E, we have 5 times the square root of 40. So 40/36 would be the largest square root that's less than 40. And if I try 40 divided by 36, so again, it's going to be the number under the radical divided by the perfect square. That would be like 1.1 repeating. That's not good. We want an integer. 3625 would be the next possibility. And we get 1.6. So that doesn't work. 16 is the next possibility. And we would get 2.5. That doesn't work. The next one would be 9. 40 divided by 9 would be 4.4 repeating. That doesn't work. The next one would be 4. 40 is evenly divisible by 4. 40 divided by 4 is 10. The square root of 4 is 2. So I get 10 root 10. Now, one reason that I like to start with the largest and work my way down is if I started, well, in this case, it wouldn't matter. It would still come out all right. 72, it wouldn't have worked. If I started with the smaller ones and worked my way up, 4 would work, but then I'd have to check other things. So using the largest one and working your way down works really well. Square root of 99. Excuse me. So 81 is the largest perfect square less than 99. 99 is not evenly divisible by 81. Then we would have 64. 99 is not evenly divisible by 64. After 64 would be 49, and it's so close. 99 divided by 49 would be 2 and 1 over 49, so almost there, but 49 doesn't work. Then 36. 99 divided by 36 doesn't come out exact, doesn't come out as an integer, so we can't use 36. 25. This is the hard part of this method. And 99 divided by 25 is very close, but not quite. 16. So then 16. 16 doesn't work. Then 9. 9 works. 9 goes into 99 divided by 9 is 11. So we get 3 times the square root of 11. So whether you like the tree method or the perfect square method, you can use whichever. They both work. So I'm going to have you try a couple on your own. Oh, sorry. First, I'm going to have you do a quick write. Then I'm going to have you try a couple on your own. So which method do you prefer? And then summarize how you simplify a radical using that method. right. And so hopefully those of you that have your packets saw, yep, we have a couple of examples to go through. So again, I'm going to give you a few minutes and then we'll take a look at those answers as well. If you have questions, don't be afraid to use the chat. All right, a couple to try here. I'm going to do the perfect square method on number 1, and then I'll do the tree method on number 2. If you did them the other way, great. You can see, both ways. It's not a bad idea. So 98, largest perfect square would be 81. 98 divided by 81 doesn't work. The next largest would be 64. 98 divided by 64 doesn't work. The next largest would be 49. 98 divided by 49 is 2. That's a good number. So I have 49 and 2. The square root of 49 is 7. We can't forget that 4 that was out front. 4 times 7 is 28. Square root 2. 261 is not evenly divisible by 2 because it's not even. But if I add the digits, 2 plus 6 is 8, plus 1 is 9. That means 3 is going to be a factor because 9 is evenly divisible by 3. And if we try 3 into 261, we would get 87. 87 is evenly divisible by 3 because if I add the digits, they add to 15. 15 is evenly divisible by 3. So 3 and 29, I think is right. I'm going to try to rewrite it so that it, doesn't look like 79. Okay. 29 is a prime number. It is only divisible by 1 and itself. So I'm done. That's the factor tree. There's my pair. So I would have a 3 outside. There's my non-pair, 29 inside. And there's my answer. Such a large number underneath the square root, and really not much we can do to simplify it. Questions? One other concept today, and that's a concept of multiplication. And we've kind of used it in that perfect square method for simplifying a radical. But what the multiplication property says is if I have something under a radical that's being multiplied, I can change that into the first factor under a radical times the second factor under a radical. So it works going this way. Because it's equal, it also works going back the other way. So if I have 2 square roots that are being multiplied, I can multiply the numbers underneath the radical and put the answer underneath the square root. Okay. So in letter A, I can multiply the 3 and the 21. And now finding the simplified version. If I use the factor tree, 2 is not going to be a factor because it's not even. Pretty clear that 3 is a factor. That's what we multiplied 21 by to get 63. 21, if I add the digits, that adds to 3, so it will be evenly divisible by 3. I have a pair of 3s for factor. And I have a 7 that doesn't have a pair to go with, so that stays underneath the square root symbol. Letter B. Here again, a little bit of a difference. We have numbers out front and numbers underneath. And the multiplication works this way. We multiply the numbers that are out front, so we can multiply the 4 and the 2. And underneath, we multiply the numbers that are underneath. 5 times 3. If I use my perfect square method, 9 is the largest perfect square that's less than 15. But 15 divided by 9 gives me 1.6 repeating, so that doesn't come out even. 4 is the next perfect square, and 15 divided by 4 gives me 3.75, not even. The only other perfect square is 1. So that means 15 can't be simplified any further. This is the simplest form. All right. Again, one for you to try. All right. So again, we have a 3 here. It's kind of understood like there's a 1 in front of this radical. Would really help if I could draw a 1 and make it look like a 1. There we go. So we get 3 times 1, which is 3. Inside the radical, 6 times 10, which is 60. Using the square or the factor tree method, 60 is even, so 2 divides evenly into 60. It goes 30 times. 30 is even, 2 divides into 30, 15 times. 15 is not even, so 2 is not a factor. But if we add the digits, it adds to 6, so 3 is a factor. And 5 is a prime number as well. So we have a perfect square factor and 2 non-perfect square factors. Don't forget the 3 that's out in front. So we have 3 times 2 outside of the radical, and inside the radical, 3 times 5. 3 times 2 is 6. 3 times 5, 15. All right. Homework is posted.